useful with those few points, I suppose. You
Yes,
would have needed the beginning of the
stuff.
evolution, which is lost.
Yes, but they actually, even if they were few data, they were useful for the inference of the jet brake, because we, I can show you the, let me go back just quickly. This, so if you see here the data, they are after 12 hours. With these points, we kind of constrained the temporal slope here, which was is in fact very consistent with our optical data here. So we use those data for that. Yeah, it's a shame that we missed the whole thing, but yeah, even though they were
okay.
useful.
Thank you. It's a pity that we have missed the early X-rays, because it would have provided very useful information. Unfortunately, we don't have them. Thank you very much.
We do better with the so now it's time.
Let's hope for the best.
Yes, you. Okay, now we can go to the Mediterranean Sea with Godefroy. I think,
yes, yeah. Let me share my screen.
So, Godefroy, you have 15 minutes.
Okay. Okay. Yeah, can you see my slides full size?
Yes, it's perfect.
Okay, great. So let's go. So I'm Godefroy Vannoye, a PhD student at CPPM, and yeah, today I will present to you how we monitor the neutrino sky for the next galactic supernova. So first I will talk a bit about core collapse supernovae and what kind of objects they are. So a really simplified explanation. They are explosive phenomena that happen at the end of the lives of massive stars, and it happens with an enormous energy release. And the basic physics behind it is that at the end of the life, the star will have an iron core, and in this iron core there will be two processes, iron photodissociation and electron capture, that will diminish the electron density and thus the electron degeneracy pressure. And once the density is low enough, there is a collapse of the core, and then the propagation of a shock wave. So why are supernovae interesting, and especially why detecting supernovae neutrinos is interesting? So first, because it would be something kind of new. To this day, we have only observed 20 neutrino coming from a supernova in 1987, where we can see the remnant on the left. And there is also a lot of interesting physics behind supernovae formation, and understanding it would bring us a lot of knowledge in astrophysics and nuclear physics. And neutrino also play a key role in the formation, so we need to detect them in order to understand these processes. Its supernovae are also really interesting because they emit multiple kind of signals. So neutrinos that happened first, and gravitational waves and electromagnetic emission. And the neutrinos, they can be used as an alert for gravitational waves and electromagnetic follow-up. So what happens for the electromagnetic radiation is that the medium of the star is too dense for light to go through, so only neutrinos can escape, and this is why we can see electromagnetic neutrinos. This is why we can see neutrinos before electromagnetic. So for the electromagnetic signals, so as we can see on the left, we observe the neutrino bursts that last for a few seconds and a few minutes, but it can go up to a few days. there is what we call the shock breakout, which is the release of the photons when the supernova shock breaks out of the surface of the star. And it can last for a few seconds to a few hours, and then there is a plateau that will last for a few months. So the photon emission will peak in soft X-rays and UV, but depending on the position of the progenitor in the galaxy, so if it's behind the galactic center, the absorption can cause the observed brightness peak to shift to optical and near ER. So here we can see on the figure on the bottom that if the supernova happens behind the galactic center, so the Earth is here, we will have a visible magnitude only in near infrared. Now for the neutrino emission, it is important to know that there is 99% of the energy that is released are low energy neutrinos, around 10 eV, in 3 phases. First, an electron neutrino burst, followed by an accretion phase, during which there is also anti-electron neutrino and neutrino of all flavors that are emitted, and a cooling phase. So with chemistry.net, we are sensitive to anti-neutrino electron via inverse petal decay. As we can see, we have a detection time window of around 500 milliseconds. So we need an automated process in order to detect those supernovae. So how do we detect neutrinos with chemistry.net, and how do we detect supernova neutrinos with chemistry.net? So first, what is chemistry.net? It's a water Cherenkov neutrino detector that is currently in construction at the bottom of American Sea. So there are 2 sites, Orca with a denser array offshore Toulon, and it's optimized for the detection of the neutrino in the 10 of GeV, and Arca with a higher volume, which is optimized for the detection of neutrinos in the TeV to PeV energy range, which is offshore the Sicily. The way the detector works is by using elemental bricks called digital optical module, or DOMs, which are spheres hosting 31 photomultipliers. And we assemble the DOMs in what we call detection units, which are lines of 18 DOMs. And what we do is we deploy those lines on the seabed in building blocks comprised of 115 DUs. So Orca will be made of 1 building block and Arca of 2 building blocks. Then how do we detect neutrinos in the energy range that we detect? So first, there is a neutrino detection, is a charge current or neutral current, and whether the generated lepton is a muon, there is a trax, or an electron, there is a shower. And then there is an electromagnetic radiation emitted in the sea called Cherenkov radiation. And by detecting this induced light with the 3D array of photomultipliers in the building block, we're able to reconstruct the neutrino properties, so trajectory, energy, and flavor. If you pay attention for supernova neutrino, we are in the tens of MeV energy range. So it makes really small tracks of a few centimeters, and the reconstruction of individual events using multiple DOMs, as we could see here, is impossible. So what we do instead is that we search for an excess of heat coincidence above the optical background. That is, so the optical background will be comprised of radioactive decay, so mostly potassium decay in seawater, bioluminescence, and atmospheric muons. But by successfully searching for an excess of heat for optimized what we call multiplicity, which is a number of photomultiplier in the DOMs that see an event, we are able to have a good detection sensitivity. So because we work with low energy neutrino and small cross section, we are only able to detect galactic or near galactic events, but we are able to detect them up to 10 sigma, depending of the size of the progenitor, of the supernova progenitor. And it's also good to know that there is an expected rate of 1.5 galactic or near galactic supernova per century. And so, yeah, the last one was in 1987, but it was not a classic core collapse. And I think the one before was during Galilean time. So the next one should be in our lifetime, and we need to be ready for it. So now that we have seen that KM3net can detect supernova, I should mention that it is not a lot. It is not the only neutrino detector that can do that. It is included in a network that connects different neutrino detectors. And the way this network works is that if at least 2 neutrino detectors send an alert in less than 10 seconds, the SNUS network for supernova early warning system will send a combined alert publicly to the astronomy community with a false alert rate of below 1% really. And here you can see the list of detectors taking part in this news. Okay, now we have seen that neutrino detectors are able to detect supernovae. What other information can we bring? So by doing what we call light curve analysis and computing light curve, which is computing higher statistic of coincidence to be able to perform time analysis, we are able to make to get some more information. So those information can be parameters estimation, like the distance and the progenitor mass. So we can see here that with higher progenitor mass, the light curve, we will see more events. We can also make constraint of models, like so by seeing some oscillation, we are able to modelize more precisely asymmetric hydrodynamic motions in the core. And one other thing that can be done is the precise fit of the arrival time of the neutrinos. And this can be done in order to do triangulation. So with neutrino detector, it is possible to get the explosion time at a millisecond level, which is not possible otherwise. And by getting this arrival time with multiple detectors, we can perform triangulation. So here on the left, we can see an example of triangulation between 4 detectors, IceCube and 3net only with ARCA, Hypermutande and Juno. And by doing this triangulation, we have an estimated angular area of around 70 square degrees, which is competitive with what Hypermutande is able to do alone by looking at the electron scattering channel, which is also around 70 square degrees. And it is also important to know that with more detectors, there will be an improvement of this angular area. And also by doing a cross match with supernova candidates, we're able to pinpoint precisely in order to make a follow-up optical observation, will give us a lot of information. To do that, there is a new network which is being developed called SNUS 2.0, which is an upgrade to SNUS, which has 3 main goals. First, to modernize the alert system to be compatible with other multi-messenger network. Also to give multiple thresholds, so not only to have 1 per century alert threshold, but to do some testing and see that it is constantly working, and also to provide subscriber with a choose your own threshold. And finally, to be able to do those light curve combination in real time and to extract physics in order to triangulate the signal in the event of a supernova. So this is my conclusion. So by combining ARCA and ORCA, we are able, with ChemistryNet, to detect the next galactic explosion with a 5 sigma discovery potential. And ChemistryNet is currently connecting to the SNEWS network, whose purpose is to find coincidence between neutrino detectors and communicate the result to the community in the event of a coincidence. We are also computing light curves when we reach high enough significance, and those light curves will be automatically transmitted to the SNEWS 2.0 soon. And this will allow us to measure parameters, constraint models of supernova position, and precisely measure the arrival time to triangulate the source signal and make a follow-up observation. So if you have any question, feel free to ask them. My last slide is a 3 article where you can find more if you want.
Okay, thank you very much. And I will come back with your last slide, you will see, the conclusion of the meeting. There is some questions. I don't see. I have one. How your follow-up is organized with SNU, with your network, with your alert system?
So for now,
how it works?
For now, SNEWS only send a SNEWS alert, I think, on GCN to say that we have had coincidences. And for the future, it's not defined how we will transmit the information yet.
So there is nothing special organized. So there is a risk that you send the alert and nothing happens.
Yes. But I think that the SNEWS has also some partners for optical follow-up, but I'm not really sure in that.
No, it's a difficult question. The answer is not easy. So
I can try to answer on this. So so for SNEWS 1.0, what we have now, there is no follow-up at all organized. We send the alert and for 2.0, we want to organize some follow-up, or at least the beginning of the follow-up. And for this, there are two ways. The first one is there are some agreement with the network, for example, you know quite well, Gamma and also this growth in the US, and they want to make a partnership with them to organize the follow-up. So the alert will be public, no problem. And then they are discussing quite a lot to develop with amateur astronomers, because they are doing quite a lot of things, and this AAVSO, this American Astronomer Society, are quite well organized to follow this kind of event. And right now what they are doing, and they are following the light curve of near star. So we know, for example, if you take to a few kiloparsecs, the number of potential stars are quite low, quite reasonable. And so on this, it's the first the first view of this problem. So, for example, for Betelgeuse, it's, you know, that there have been some excitement a few years ago, but that's what we are doing right now.
Okay, and SNews is plugged to AstroColibri. Maybe it is. I've missed this, but
the public GCN. So AstroColibri is connected to the GCN. So
yes, I know. Yes, but how AstroColibri is managing this?
If we get an alert, you will get plenty of notifications.
Okay.
Just in case to not miss it.
Okay. But it's not qualifying in your type of events. I see gravitational wave, neutrino, burst.
Because we didn't have an alert yet, right? We still wait for the next supernova.
Oh, yeah, okay. So
yeah, there has been no false alert to this day.
Okay. Okay, it's a good comment. Excellent. Okay, thanks. Thank you very much.
You're welcome.
It's nice to see.